All right, so very good. Let's just jump right in there. So we're going to spend some time, actually in Chapter 3, talking about different temperatures at different locations. But why does temperature change? Well, temperature can change because of your location to your location. And we'll talk more about location. But for instance, if you're near the equator, it's generally warmer. If you're near the poles, it's generally colder. Of course, those locations are what we call latitude. So let me grab the globe here. Okay, so the lines of latitude, what latitude is the equator?
0.
0, very good, it's 0 latitude. And it goes all the way up to 90. So actually there are rings kind of marked on the Earth to say what latitude you're at. We're about, I think, 42 or so. 42 degrees north latitude. And then here it goes south, okay? And then if you get to the poles you're at, do you know what latitude that is? Remember? 90. If you get to the pole, you're at 90 degrees latitude. And you're 0, and then down here you're at 90 degrees south latitude. Okay, so latitude can affect what your temperature is. What else can affect your temperature? Well, where you're at as you orbit the sun. So today we're going to use this as the sun, and of course here's the Earth. Okay, so we know that as the Earth orbits the sun, that's what gives us seasons. We'll be talking more about that. Okay. Another thing that gives you different temperatures, okay, is this idea of air masses that we kind of just now talked about. A chunk of air, basically from the north, becomes cold and moves down, makes us cold. A chunk of air that hangs about a couple weeks south of us, moves up, and it makes us warm. Okay, so that's air masses can kind of change our temperatures too. So we need to talk about the two motions of the Earth, something that you're probably already very familiar with. Okay, the Earth spins on its axis of rotation once every about 24 hours. Okay, now its axis of rotation is tilted, so I don't know if you can kind of see. When you buy a globe, here's the north axis of rotation, here's the south axis of rotation, so it's actually tilted. And it's tilted, what we say, 23.5 degrees. So that 23.5 degrees actually comes from, if it was straight up, okay, you tilt it 23.5 degrees. So that's the angle we're talking about right there, the tilted axis of rotation. And they think, by the way, that the Earth got tilted a long time ago, early on in when it first became an Earth. There was extra stuff in the solar system. We kind of talked about the bombardment. That's how we got our nitrogen. And probably something about the size of Mars hit the Earth, caused it to tilt, and form the moon about the same time. That is so cool. So we're tilted. It gives us seasons.
If the Earth were right up, would we be all melted?
If the Earth was straight up and down, I don't know about melted. I have to think about it. But I do know that we would not have seasons. So basically, here in the Midwest, we'd have a constant climate. It wouldn't change throughout the year. So the poles would always be frozen, and we'd still kind of have that sort of gradient. So the Earth spins once on its axis every 24 hours. The Earth orbits the sun, and we call that revolution. The Earth orbits the sun. We call that revolution. Rotation is it spinning on its tilted axis of rotation. Revolution is it orbiting the sun. And we have a leap year coming, like this year. So actually, it takes, as the Earth goes around the sun, it takes 365 1/4 days. So every 4 years, we have an extra day, which we have this year. So February, instead of having 28 days, it has 29 days. Can you imagine if you were born on February 29th? Be like, your birthday would only come around every 4 years.
It's sad.
That is sad.
I'd make it 28.
I don't know how that would work. Yeah, make you
They
feel.
celebrate their birthday like March 1st.
Do they? They must do something.
Or else they'd just be turning like 5.
Yeah, I agree. So down here, you see a diagram of the sun with the Earth orbiting the sun. My stylus. So as the Earth orbits the sun, it's kind of off center. So let's see. Actually, the sun is a little bit off center. It's actually, here we are a little bit closer. The Earth is a little bit closer to the sun, and we call this perihelion. Okay, and notice the time of year. Okay, about January 3rd, we're at perihelion. We just kind of celebrated perihelion. And yet in January, we're actually in winter. Okay, when we're in winter, though, what is the southern hemisphere experiencing? Summer, exactly. And we're going to talk more about seasons, but can you guys already see, if you look at this position of the Earth and the tilted axis of rotation? Okay, so here's my tilt. It's kind of slanted that way. So actually this would be kind of what that's showing. By the way, our North Pole, our north axis of rotation, points to a special star. What's that special star? The North Star, exactly, Polaris. So this diagram does a pretty good job of kind of showing you how this works. Now, the Earth's orbit is counterclockwise. So with all of us with your fancy phones that are analog phones, but if you look at the face of a clock goes 1, 2, 3, 4, 5, 6, right? So counterclockwise would be this way. So counterclockwise, the Earth goes around the sun counterclockwise like this. But now here's the deal. Can you see how this tilt is always towards Polaris? Okay. So I said this is January 3rd or so, okay, and it's counterclockwise. So this would be 3 months later. Okay, this would be 3 months after that. I'm always pointing that way. Of course, we're doing this once every 24 hours. This is 6 months away from where I started. Okay, and this is another 3 months after that. Okay. Now, as this is tilted, we'll be talking more about this, but as this is tilted, can you see that the sun, this is the sun shining on here, basically what we call a circle of illumination, it doesn't. If you are north of, we're going to call it the Arctic Circle, if you're north of the Arctic Circle, you don't, as the Earth spins, you don't get any daylight. And you can actually kind of see it in there too. So that's perihelion, and then 6 months later, it's at aphelion. Okay, aphelion is this one. And that is where it is farthest from the sun. Now, I've had students sometimes say, well, if they are, for instance, let's pick on aphelion. So this is farthest. Of course, in July, we are like in the dead of summer, right? Sometimes students will say, well, since it's summer for us, but of course it's winter for the southern hemisphere. And you're like, well, if it's winter when it's furthest away, are their winters more exaggerated? And I don't think so. Okay, but I do think the southern hemisphere has something going for it, and that is that it has the majority of water, large bodies of water like the oceans, kind of heavy in the southern hemisphere. And that's probably more of an effect than this is. So one last thing on the slide, it's a busy slide, is this thing called the plane of the ecliptic. Okay, so as I up here kind of do the whole Earth orbiting the sun thing, okay, I could actually, and I guess you only need 3 points to make a plane, but actually kind of this frisbee here, okay, this is the plane of the ecliptic. Did you guys hear, I bet you did, where they found a 9th planet? They think evidence, we don't have any pictures of the 9th planet, there's an artist's rendition of the 9th planet. They think the 9th planet is kind of similar to our last 2 planets, the blue ones, Uranus and Neptune. They think that 9th one is kind of like that. But the 9th one, I know.
How far do they think it is from Pluto? Like to
I don't know how far, but the farther a planet is from the sun, the longer it takes to complete one orbit. Not just because its circle is bigger, but because gravitationally speaking, it moves more slowly in its orbit. So to kind of tell you how far it must be, it takes somewhere between 10,000 to 20,000 years for it to go once around the sun. Is that not cool or what? That is so exciting, I know. So.
I'm confused. Okay, so July 4th is farthest from the sun. I always thought it was the opposite of that, because I figured summer you'd think we're closer.
I know.
Is it because of the axis?
It's because the axis, exactly. He's wondering, because over here, we are at aphelion, so we're a little bit farther away, okay? But it's because, and we'll talk more about that, but one of the things is over here, actually, if you're above the Arctic Circle as the Earth completes one day, you don't have nighttime. So you have more daylight hours. But the other thing is the sun is more direct,
Okay.
okay? And the sun down here is kind of at an angle, a low angle. So, but yeah, it is, it's backwards from what you think. Yeah. Yep. Very good. Okay. So it's hard to see, but lines of latitude. So we said the equator is 0 latitude, and it goes up. We're about, what did I say, about 42 latitude. Okay, go on up, and this is 90 degrees latitude. Now, I was always kind of interested about 90 degrees latitude. That's like right at the top. So how big is that circle? Well, it's more of a point, 90 degrees latitude, North Pole. Okay, 90 degrees south latitude, South Pole. But there are lines of latitude that you kind of need to know for meteorology, and they're listed here. It's kind of hard to see. But, of course, the equator was 0. Oh, 0 degrees Celsius, sorry. 0 degrees latitude. That's the equator. Okay. And then at 23.5 degrees north latitude, I better put an N there for north, we have the first of 2 tropics. We have the Tropic of Cancer at 23.5. Now, I already said 23.5 just a little bit ago. 23.5, it's not a coincidence that 23.5 is also the tilt of the Earth's axis of rotation. So that's a special line of latitude, and this globe up here actually has a ... for 23.5 degrees north latitude. And then if you keep going up, you'll pass us. Okay, you could go up to 66.5 degrees north latitude, and you'd hit the Arctic Circle. And that is kind of where I said, like, if you're over here and the Earth spins around, if you're above the Arctic Circle, you don't get any daylight. Okay? If you're over there in the dead of summer and the Earth spins around, the sun never sets above the Arctic Circle. This is where I kind of teased there, like, if the whole vampire thing, there's a vampire movie out there that talks about how the vampires go to the North Pole because, yeah. And then down here, we have the second tropic. This is still 23.5 degrees south latitude. And that's the Tropic of Capricorn. I kind of remember the 2 tropics because I think we get corns on our feet. I don't know. So Tropic of Capricorn is the south and southern hemisphere. And then not listed on here, but I think it should be, actually here, and kind of analogous to our Arctic Circle, is the Antarctic Circle. So this would be 66.5 degrees south latitude, and that's the Antarctic Circle. Okay. So those are special lines of latitude that you'll hear us refer to. Okay. Notice the 2 equinoxes and 2 solstices. Okay. So you're going to have to kind of erase the January 4th a little bit. Okay. So the important date instead of January 4th when we're at perihelion actually is December 21st, so a few weeks earlier than that. You guys would probably tell me that's the beginning of winter, kind of, December 21st. So December 21st, we are here. Our axis of rotation, again, pointed to Polaris. And by the way, when I'm in this room, that clock does pretty good for Polaris. Kind of a little bit off, but that's kind of Polaris. That's like our North Star. Okay? Okay. So it takes 12 months to go around the sun once. Okay, so if you divide 12 into 4 segments, you got 3 months apart. Okay, so it takes 3 months to go 1/4 of the way around. Okay, so actually this December 21st is one of our 2 solstices. This is the winter solstice for the northern hemisphere. Okay, winter solstice here. Okay, and then let's go 6 months. Okay, there's 3, and there's 6 months later. Okay, this actually is the summer solstice. So, and I'm bad about memorizing, is it the 21st, 22nd, or 23rd of these months? I just say it's somewhere between the 21st and the 23rd. So that one's December, 21st to the 23rd. This one is June. Okay, this is our summer solstice, June 21st to 23rd. Okay. So in between our two solstices, we have the equinoxes. So here we go. This is December 21st, 23rd. Okay. 3 months later, that's March. And that actually is one of my favorite times of year. That's spring. Okay. Fall's awesome too. Okay. And then we have our winter solstice. Okay. And then we have our second equinox. Okay. Here's a figure from your textbook just for the northern hemisphere. For the solstices and the equinoxes. All right. So this is when they occur. When they occur. Okay. We'll be talking more about, it's not the proximity of the Earth to the Sun, it's kind of how it's tilted that gives us our seasons. And the tilt actually has consequences for how kind of straight or how slanted the rays of the sun are. So at the summer solstice, our northern hemisphere summer solstice, who gets the most direct rays? It's the Tropic of Cancer. Okay. At our winter solstice, who gets the most direct rays? It's in the southern hemisphere. It's the Tropic of Capricorn. For both the equinoxes, who gets the direct rays? It's 0 degrees latitude. It's right over the equator. Now, I'll kind of pick on equinoxes. The reason they're called equinoxes is that here, and 6 months later, we call this spring, right? This is the spring equinox. Actually, that sheet of light that's coming from the sun, as the Earth spins, all latitudes get equal daylight and equal nighttime. That's why they're called equinoxes. 12 hours of light, 12 hours of dark. Okay. As we start to go over here, this starts to kind of exaggerate the number of daylight hours the northern hemisphere gets and minimize kind of the number of daylight hours the southern hemisphere gets, because they're kind of getting ready to kind of like that, okay? So on the equinoxes, equal day and equal night. So we'll talk about that next line coming up. All right, so this looks like summer in the northern hemisphere. If it's a dead solstice, that would be maybe June 21st. Okay, summer solstice. This photograph over here is kind of a time-lapsed photo of where the sun's position is if you are north of the Mason-Dixon line. No, if you are north of the Arctic Circle. How does the sun, okay, go in the sky? Now, what you're looking at here is actually a sunset. The sun does not set at the summer solstice if you're in the northern hemisphere. So this actually would be, and I'm sure there's songs written about this, this is actually the midnight sun. That is midnight right there. It just doesn't set. That would be strange. I don't know how you'd sleep.
You get really dark curtains.
Yeah, you would. You would have to do something, because...
Yeah, guy had to do it on Survivor Man. Sleep in the Arctic Circle.
He
You just have to, like, shelter yourself from the sun.
and Survivor Man, yeah.
Obviously, your biological clock is kind of funked up.
It would be, yeah, it would be really weird.
You'd be tired, but you wouldn't know why because the sun's out.
Yep. But then the problem is, you'd have that extreme in the summer solstice, but at the winter solstice, you'd have the other extreme where the sun doesn't rise. Oh my gosh.
I think that'd be worse. Oh, yeah.
That would be bad. I would be.
And plus, your body wakes up to the sunlight in the morning, part of your sleep system. So I don't know if you'd wake up at normal times.
I just, she's like, I can handle it. I don't know. What's that? Okay. So this is the other exaggeration. So that would be the other solstice. So that's the winter solstice there on the right. Okay. And on these lines of latitude, in these figures, they've drawn like how many hours of sunlight you get. Okay, so there's 24 hours, you get 15 hours, you get 13 hours kind of in Mexico. Okay, you get 9 hours kind of at this latitude. So those are the two solstices, the summer and the winter solstice for us anyway. And the two equinoxes would look like this. Okay. Whereas the Earth spins, the reason they call them equinoxes is we have equal amount of daylight and nighttime for all lines of latitude. And the term, I put it, emphasize it whenever they talk about the circle of illumination, that actually is just kind of where, you know, this is the day and this is the night. The circle of illumination for that, at that time, coming from the sun.
So they draw it as hardly any discrepancy between the light and the day, but is it possible to be standing in the light and see the dark? I mean, I don't think so. That wouldn't be possible.
Is it possible to be standing in the light and to see the dark?
Yeah, that's probably.
It's weird.
That's a stupid question.
No. You know what comes to mind? Maybe this is what you were thinking of too. Like the International Space Station, they are hovering above, and they can actually see the daytime and the nighttime, and the kind of shadow coming over the daytime.
But you'd have to be high enough to see.
Yeah, you'd have to be high enough.
Yeah.
Yeah. Sounds like a science fiction movie or something. So over here is a figure from your textbook, kind of saying the same things. Now the one thing, and I've chased it down a little bit because it just really bothers me. Now I understand if you're at 90 degrees latitude, you know, you're like on a pole, you know, North Pole here or the South Pole here if you're at 90 degrees latitude. But what they're saying is that at the summer solstice you have 6 months of daylight. I just don't quite understand that. Can't wrap my head around that. But I've kind of seen similar things on the internet. I'm just throwing it out there. But aside from that weird latitude, I mean, these normal latitudes kind of make sense to me. How, well, except for that one, but how the your number of daylight hours increase as you go towards the pole. And the equinoxes. Okay, so don't worry about the 6 month thing. Worry about things like the equinoxes. You get 12 hours of daylight regardless of your latitude. All right. So angle, right? Angle. So you guys probably would tell me that at noon, like when it's in the dead of winter, have you ever kind of watched the sun kind of do its thing in the dead of winter? It doesn't get very high even at noon. It kind of goes up and then it sets. It rises in the east, and then it sets in the west. But it doesn't get very high, okay? Compare that to, like, the dead of summer, okay? In the summertime, the sun's out longer, and it gets, at noon, it's higher in the sky. Rises in the east, gets high in the sky at noon, and then sets, okay? So kind of between the winter solstice and the summer solstice, we basically, if we were going to look at the noontime sun, it would kind of go like this. It would have a what we call a low angle, okay, and then it would have the highest angle at the summer solstice, and then it would start going back down again at noon, or noontime sun. And so these are kind of showing you the noontime sun. Now when they talk about an angle of the sun, basically what you do is you take one hand and you shove it out to the horizon, and you take the other hand, you kind of make a vertex with your elbows, and you kind of point to where the sun is. And so kind of that angle that's right there, that actually is the angle we're talking about. Okay? So we have a low angle, and then we have a high angle. This would be our winter solstice, this would be our summer solstice. Okay? All right, so you probably buy the whole angle thing.
So what happens when you see the sun and the moon at the same time?
When you see the sun and the moon at the same time, all it is we can kind of leave this configuration. All it means is if my fist is the moon goes around the Earth counterclockwise, so like this, right? It goes counterclockwise. And it goes like once every month, okay? So basically, if you see the sun and the moon, it just means that the moon just happens to kind of be there. Yeah, and then the moon will go back around. So it's quite possible to see the sun and the moon. Now the moon's over
cool
here.
because if you look on one side, you
That
see
is
the
neat.
moon, and then you see the sun
Yeah,
on the
I do
side.
like
It's just
that.
like,
It is neat to see those two celestial bodies. And the cool thing about the sun and the moon is they have similar like sizes of disks. And so that actually lends us to have the eclipses that we enjoy too. But yeah, I agree. You're like, hey, wait a minute. There's the sun, there's the moon. Yeah. Okay. So this is picking about 40 degrees north latitude, which is a little bit south of us. Okay. 40 degrees. These go every.
Is it 66 miles every degree?
What's that?
Is it 66 miles every degree?
I'm not sure, but it would be a constant amount. To look it up. So about in here, okay, your noontime sun would be, like we were talking about, the angle would be higher at the summer solstice and lower at the winter solstice at noon. Okay, I bet you're okay with that. This actually then is at the equinoxes. The equinoxes, the angle should be somewhere in between. So your author's gone ahead and given you those angles. So here we have the highest angle at the summer solstice looks like 73.5. At the winter solstice, only gets as high as 26.5. And at the equinoxes, it's between. That makes sense. So then the other thing your author did was to switch it up a little bit to change from 40 degrees north latitude to 80 degrees north latitude. Okay, not only 80 degrees north latitude, but went ahead and picked the summer solstice. Okay, so the summer solstice, remember I said if on the summer solstice, which is over here, if you're fortunate to be above, and it's kind of a dotted line here, above the Arctic Circle, okay, which is 66.5 degrees. So 80 degrees is above the Arctic Circle, okay? As the Earth spins, you're not ever going to have nighttime. You just aren't. So that's actually what's being shown here. Oop, better not put down some. Okay, here's the noontime sun, okay? The sun then rises in the east, it sets in the west. As the sun sets, notice that actually here in the north, it doesn't go below the horizon. Okay, it goes low, kind of like we saw on that photo. Okay, but then it rises back up again. So you don't have any night. So if you're a party animal, it could go either way. So, isn't that cool? Anyway, okay. All right, so who cares about the angle? So there are two things that care about the angle and that affect basically how much energy we're going to get. So two things that have to do with the angle is beam spreading and beam depletion. They both have the word beam in them. So remember, we have our greatest angle at the solstices, or excuse me, at the summer solstice. So beam spreading looks like this. If you were to take a flashlight and just hover it over a piece of paper, okay, the angle you're making with the piece of paper would be, what do you think the angle is? I think it's 90 degrees too. You're making the biggest angle you can, 90 degrees. Okay. If you were to take it and to go ahead and kind of slant it like you see here, I'm maybe liking this. We'll call this 45. Yeah, that's what I think too. So we have a 90 degree angle and a 45 degree angle. So in both cases, your flashlight is behaving normally. In the case where the angle is the greatest, notice that the energy coming from your flashlight has this area. I'll call this A1 for that area. When it's at a slant with a smaller angle, it has your same beam spreads out to this area. What would you say about areas A1 and A2?
That one would have more light.
A2 is spread out more. A2 has more light spread over more of the paper. Yep. So that actually is beam spreading. And it happens when you have a smaller angle. So then I think I have the captions here. Smaller angle, more beam spreading. Okay. A larger angle, less beam spreading. You'll hear people, in fact me, say that actually this situation up here where you have the greatest angle, that is the most direct rays. Most direct, I'll just put E for energy, most direct. Okay, so let's go back to kind of the Earth. And at the equinoxes, we said that the most direct rays actually is over the equator. So here, this could be at an equinox, okay? But basically, the way this works is you take one shaft of light. We could take this particular shaft of light, okay? And we say that shaft of light hits the Earth, and it's spread 1 unit. It's not really much spread. Now, if we change from the equator to here in the Midwest, notice the barn, okay? We're back in Iowa. Okay, so we go from the equator to 40 degrees north latitude. We are going to have the rays that come from the sun are going to be more at an angle. The sun is not going to be as high at noon to us. Okay, so when we go out and find the sun, instead of being like this, like the equator, it's going to be like this. But we can look at that angle, okay, and it'll be smaller than 90. It's 90 with at the equator. And so then actually, if we want to look at this phenomenon of beam spreading, we can go ahead and pick these rays, okay? When they strike the Earth's surface, they're going to be at an angle. And now instead of 1 unit of Earth, it's that same energy is going to heat up 1.4 units of Earth. We go ahead and kind of take that one step further, going up farther north, okay? Where at noon, the same day, the sun won't rise as high at noon. Okay, so this was the tropics, this was us, and this is like near the poles, where the angle is even less. So with a smaller angle, then we have that same beam of light that hit the equator and hit us here in the Midwest. Now instead of spreading 1 or 1.4, it's spreading 2 units as it hits the Earth's surface. That's called beam spreading. Good. Okay, so I told you there were 2 reasons that angle makes a difference. One of it's beam spreading, so the smaller the angle, the more that beam is spread. The other is beam depletion. And beam depletion happens because that shaft of light has to travel through the Earth's atmosphere. And we're going to talk more about, well, so a shaft of light travels through the Earth's atmosphere. What happens? Well, we'll talk more about that. But the thicker the Earth's atmosphere that it needs to travel through, the more it's going to be depleted. So we call this beam depletion. So here we go. Have kind of a couple different scenarios here. Again, this is kind of a snapshot for the same day at different latitudes. Okay, so if we pick on the equator down here, okay, notice that they're getting the most direct light from the sun. Okay, that looks like 90 to me. That's as direct as you can get. That's the biggest angle you can get. Here we have a smaller angle, and it gets smaller and smaller. Okay, the angle that the sun's making. Now, if we back to the equator, back here, this right here, this thickness of the Earth is what can be removing some of the sun's energy. Okay, so that's how thick the Earth is to remove that's the depletion that can happen there at that latitude. Does this hopefully right here, I'll call this L1, I'll call this L2. Does L2 look longer to you? Because it's supposed to. And this is L3, and this is L4. That L is basically the length of the Earth's atmosphere that the sun has to pass through. Okay, the same day. So it's beam depletion. So here's my little note to self, okay? So let's pick an equinox, okay? So an equinox, we get up March 21st, going to be here before we know it. Okay, the sun rises in the east, okay? We have our noontime sun, and it sets in the west, okay? As the sun kind of goes through its rising, okay, we could get a fix on its angle throughout the day, okay? And actually its angle throughout the given day varies. It starts out small, it gets to noon, okay, and then it goes back down again. So actually this idea of beam spreading and beam depletion actually throughout the given day happens to us, an angle thing with the sun. And it happens by latitude, and it happens as we orbit the sun too. Okay. Well, I think that's a very good place to stop. Seems like a nice change of gears. So we'll pick up here on Monday.
I just had some.